Stress. Stress occurs in any material which supports a load. Stress is the way a material transfers the load through its molecules. It's like an internal pressure resisting the external applied loads. Stress, like pressure, is force per unit area. That is, stress equals force divided by area. Remember that force is measured in units of newtons or kilonewtons, and the unit of area is square millimeters or square meters. Stress is measured in pascals, kilopascals, or megapascals. The most common unit used for structural materials is megapascals, as the other units are too small. For example, the concrete strength for a typical reinforced concrete slab is 25 megapascals. Strain. Strain is the term applied to deformation or change of shape of an object when a load is placed on it. Delicate measuring instruments such as strain gauges may be needed to detect the amount of deformation. The amount of deformation compared to the original shape is called strain and is represented by the letter E. This is a ratio which has no units. E equals change in dimension divided by original dimension. Deformation is usually denoted by D, or the symbol delta, and generally refers to small deformations. For example, the strain in a beam under load is the change in length compared to the original length measured in millimeters. Types of stress. The term stress can be used in many ways, with many forms of stress occurring throughout structures. Tensile stress. Tensile stress is when a member is subject to tension forces. A diagram is shown below of a member, a long rectangular box shape, with forces indicated by arrows extending outwards at either end of the member. Compressive. Compressive stress is when a member is subject to compressive forces. This diagram is of a member, a long rectangular box shape, with forces pushing inwards at both ends. Shear. Shear stress is the shearing action of vertical loads and horizontal shearing due to bending. The region of shear is parallel to the direction of force. This diagram shows the shear stresses in a bolt caused by the bar attached to it. Tension stresses act within the bolt, pulling outwards in both directions along its length. Shear stresses are indicated as acting on the bolt. Bending stress occurs as a beam bends, and it is subject to a combination of compressive, tensile, and shear stresses. This diagram is shown of a member with supports at each end. The neutral axis is drawn as a dotted line along the middle of the member, running along the full length of the member. Loads are pushing down on the member, causing it to bend downwards in the middle. The upper part of the member is under compression, and the lower part of the member is under tension. Torsional stress occurs when a member is twisted along its length. Torsion is usually related to rotational twisting. Twisting moments are produced by forces which are at right angles to the plane of the structure. The center line of the structure stays straight. This diagram shows a beam supported at both ends. A load is indicated near the middle of the beam, acting downward. The beam shows distortion in this area as a result of this load. Bearing stress is the stress that develops when one structural member rests on another. This diagram is shown of a member jutting outwards from a wall. It is supported at one end only. A bearing stress is indicated underneath the member at the point where it is supported at the wall. Yield stress is the amount of stress that will cause failure of a material. Failure occurs at the value of stress at the ultimate strength. Here, a graph is shown with the vertical axis labelled stress and the horizontal axis labelled stress-strain diagram for mild steel. The graph starts at the intersection of the axis as a straight line sloping upwards to the right. Along this straight section of the graph, the point where stress equals 165 is labelled max permissible stress. At the top of this straight section, which occurs where stress equals 200, the graph bends suddenly downwards, and this point is labelled yield point. After a small straight section here, it then curves upwards again to a high point, then begins to curve downwards again. The end of this downwards curve, which occurs slightly below the maximum stress level, is labelled ultimate strength. These stresses can be calculated with a high degree of accuracy. Hence, we can predict a structural member's performance if we compare the stresses that it can take before it reaches its yield point, compared to the actual stresses it will be subject to once all the loads have been calculated. A material can still perform after yield stress. Once material is past the yield stress point, it is in the elastic zone, then it is in the plastic zone. Materials return to their original length when stressed in elastic zone, but deform once stressed past yield stress point.